several times. And it's really a good place to go.
Don't do it, huh?
Don't do it? No, do it. Good country. And his bachelor's degree is from Guatemala. And PhD is from RPI in New York State. Presently, he is a professor at KTH. He will tell us what KTH stands for. It's a horrible word in Swedish, I think, and it's in Stockholm, but he also is with Statnet, which is a Norwegian transmission operator. TSO, is that right? That's right.
Yeah.
So bienvenido a ASU.
Thank you. Gracias.
Okay.
Grazie. Okay. So Jerry introduced me. KTH is Kungliga Tekniska Högskolan. It's Royal Tekniska is technical, and Högskola is a higher learning institution. And yeah, I work for the research and development department of the transmission company in Norway. This is how I arranged this. I will not talk about me, but I will try to give you an idea of the context of why I do things and how I do them and what is the perspective that I'm coming from. I will not tell you about intermittency of solar and all of these things that everybody uses to introduce a topic. I will tell you what I really think and why I do things. I think it's important so you can understand the research topics that I have and how I organize it. So I will show you some selected results because I have a lot of projects. So I pick the ones that are pretty much ending. So you get a feeling of what I did over a few years and get some interest. Yeah, this is pretty much what Jerry said, and that's my lab. What else should I do? Yeah, okay. So I will talk a lot about modeling and simulation technologies, M&S or MS, and measurement-based methods, well as PMU things. And what I like to point out that all of these things are tools actually. So I come from that background that I am a tool developer. That's how I think about my research. I'm trying to develop new things. And it's actually the history of engineering is about doing tools. So we go from making things with rocks to using those very, very fancy transient network analyzers. I have actually seen those. To using computing, right? And that's pervasive. And one thing that I tell people is that I feel like a little bit of a caveman sometimes when I look at the tools that we use, when I compare it to my colleagues. I have friends that worked in applied math, and I was amazed by what they could do because of what was available to them. For example, if they wanted to make a new integration method or a new partial differential equation solver, they will glue software from so many places and do something new in relatively no time. And we can't really do that. We're very, very isolated from how other communities work. If you look at that difference, so I feel a little bit like a caveman when people tells me, "Oh, you haven't done that. It's 2015." So that gives you an idea. So how does the future look like? That's where I like to start. And it's very, 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 very hard to predict the future. But I divide it like this, that you will have constraints, and this is what most people in power systems start talking about. They will have uncertainty in generation and load and so on. We have climate uncertainties, right? And then we have enablers, and what you can do is that you can build infrastructure, cyber assets and physical assets, but at the end you have to operate those assets. So actually, these are the kind of tools that I'm interested in, to build tools so you can operate the system. And basically, it's like, these tools are what support the system operation. So that's what I try to do. So can anybody actually tell you what the future looks like? Do you know what this is? This is a painting made more than 100 years ago. About, I don't remember the artist, I have it in the footnotes. It's Albert Rovida, showing how the year 2000 should be. So people should be in flying cars, and there was pervasive use of electricity already, as you see. So it's very, very hard to tell what the future is, right? But we can make educated guesses and try to prepare for that. So this is one of these views. And what you see here, this is from the Fast Coexist link, website. And we already can see some of these views of the future. This is a future building. And what you can find here is that you have real-time data feeds, display of energy. We already have that today in some ways. You could get it on your phone if you have a smart meter. The other thing that we are already going there is that you see there's some generation within the integrated into the system. So you have micro wind power production and also solar. So we have these visions of the world, and we're trying to make educated guesses of how it works, but sometimes you can't really figure out where we're going. But it's good to try. So as I try to explain you how I look at the future and why I do the things that I do, we actually will have these issues, that we will have to transport more energy in a rapidly changing world. So for example, I have been reading some articles of people that, Damien Ernst, for example, from Belgium, he's proposing that we have a worldwide interconnected grid. That's completely feasible. We did it for telegraphs. We do it for the internet. So it's interesting to think about that. And regardless of where you are, these will have huge uncertainties. Okay? We will have to live with uncertainty of climate and energy availability. So, and the other thing that we have to think about, electrical power operators, okay? Transmission companies, distribution companies, the only reason they exist is because of regulation. Who says that if they say, well, why not have Google or Facebook run this? Don't you think they're perfectly capable of doing it? So how do transmission companies and distribution companies remain the operators of such critical infrastructure? Is there any future for them? This is a very interesting concept to think about, I think. So the only way that you can guarantee that you will operate this is either that you have a mandate from the government or that you're the best at it. An operation in today's world is going to be hardware and software, and more software. So we need both, because if we're going to have a lot of software, we actually need sustainable solutions for cyber components. No, very little people, few people think about software sustainability, but that's a critical thing that we have to think about. You know, your code has to compile in 50 years. Is that going to be possible? Okay, and both physical and cyber assets has to be flexible. So how do we do that? How do we build those tools and so on? So if you take a look, this is what it is more or less right now. What does that evolve to? Okay, so it's just putting some questions to think about. So how we will manage uncertainty, so we will have two types of data that we can use to take decisions. So basically we will use measurements and or simulations. Working with modeling and simulation tools, and working with sensor networks. And these tools should aim at answering critical questions that could be learned from the past. That will be learning from measurement data. You can also answer questions of what action should be taken now and what action should be taken in the future. And that means deriving information from models and simulations. So what I think in the future is you're going to have to be able to build tools and leverage on tools that are mixing both models and sensor data in a very intrinsic way, that are able to couple the two worldviews that we have. But this is actually, to be able to build this, all of it depends on the evolution of the modeling and simulation technologies that we have today and of sensor networks. How we're deciding to pick technology today has a huge impact on how we do this. So we have to keep that in mind on how we do research and develop things. This gives you an idea of what kind of tools that we're going to need for the future. So here you have sensor network data, here you have model and simulation data. In this direction is what you can learn from the past, when you can learn from data. And this direction is, as uncertainties increase, you need to be able to predict things, okay? And what is happening at this moment is what we call real-time analysis. And whatever happens from this point is what you're trying to predict to take decisions in the future. Whatever you're doing in this direction is that you're trying to learn from the past. And this is constantly moving if you think about it, right? So you can ask these questions: what happened in the past? Why did it happen? How could it be avoided? And that means to build tools with data mining, pattern recognition. You can do event reconstruction, model validation, post-mortem optimization, how we should have done this. Okay, that's called post-mortem optimization. This is what a lot of focus is right now in our communities: real-time monitoring and analysis, but you can go a little bit further to control and system protection. But as you go into the future, it's impossible to not use predictive tools. So you have to build this into your way of thinking and into your architecture from an early stage. So, yeah. So that's more or less gives you an idea of how things think. And why is this important? This is a recent picture of how technology actually has been moving us through the different industrial revolutions. So if you see, it has been a progression of being able to automate. So we have assembly lines, we have controllers, and now we have the use of cyber-physical systems. Okay? And the degree of complexity of the systems is increasing as we go over time. So, are we in our field of power engineering? Are we moving to this fourth revolution? Okay. Have our sensor networks evolved sufficiently to live in this sort of world of networked systems? Are our modeling and simulation tools prepared to fulfill the needs of cyber-physical systems? I think I'm asking more questions than I'm trying to answer, but that's the way I do it. So let's take a simple analogy that I like very much to do to explain to people that do nothing with power systems. So how do measurement sources evolve? The thing that is closest to you is to measure your weight, and I am particularly obsessed about this. I measure my weight at least 3 times a day because I have to take control of it. So we started with an analog scale. I use those. I don't know if you still use those. Then we had the first digital version of these scales where you had more. So in this case, you had only one measurement at a very uncertain time. So if you look at your watch, you could tell what it was and record the date, right? And it had limited precision, both the scale and your eyes. So there's a lot of uncertainty on the measurement there. And you went to the next version. So then you had a digital clock there. You had more points because you had this precision that your eyes probably cannot make. You had a more certain time because you had an internal clock, but the internal clock has limited accuracy actually, so we cannot measure really to the millisecond in that case. You had better precision, and the problem was that the measurements were only available locally. Then we have the next version, when you take measurements of different variables, not only your weight, but also your body mass and other things. You added some connectivity and some networking. How? By interfacing it to your laptop with a serial port or USB. the data lives in a silo, in a specialized computing program. Okay? And now this is where we are more or less today. I think I picked the wrong one because these guys are not doing what they should. But now we have a fully networked solutions where you can measure with the scale. It's set up to the network. You have full connectivity because you can access it from your phone, from your tablet, from the computer. And integration in a platform. Apple just really dealt with one of the biggest problems or developing any software application, is that data lives in silos. And now with Apple Health, you can interrelate different application data through the platform. And this is a key thing, and you will see why it affects us. But so that you see that it's not only the power system field that hasn't thought through these things, it's everywhere, right? The scale is actually secondary. It's more about the information that you have access through. So yeah, it's the sensor that you have there, but how you are able to monitor the information from the past and do projections yourself if you're doing some sort of training and so on. Yeah, so that's pretty much something that you have to think about when you look at power systems. So how these monitoring devices have evolved. This is an analog watt meter. So you get one point in time at a very uncertain time and limited precision. So if you take one of the points here, maybe you get one dot. Then we went to the digital remote terminal unit and SCADA. So you get some few points, maybe as is shown here, one there, one there. A little better precision with limited networking. Okay, you only communicate with a certain protocol. And also limited connectivity. And the data lives in a silo. And that silo is made by a corporation. So your SCADA system, if it is supported by company A, when you want to change that, you have to build the thing from scratch. So in the Norwegian company, it has taken about 5 years just to try to transition from the old EMS SCADA system to the new one. And now we have PMUs, all right, or Synchrophasor Technology. So you get a lot of points. You got exact GPS with very much more precision. You measure a lot of variables. So now you measure phasors. You don't measure power. The power is a secondary result. You measure the innate quantities. You have better connectivity, but the data lives in silos. We're still locked into particular databases with no standards for database data exchange, and you're locked into particular tool provider. So if you're outside the vendor system, good luck. You can't really make a new PMU application. All right. So that brings me to the evolution of the control room, which is very similar to what we saw before. I actually have seen rooms like this. I'm not that old, but I'm from Guatemala, so I've seen this. So this is the analog system, right? The digital version 1 is where you get some displays over here, so you could monitor certain lines. This is what we have more or less still today, where you, in the digital version 2, you actually saw the appearance of EMS applications. And that's something very important because you were able to, for example, based on the snapshot, do a contingency analysis. Okay, so that was it's a pretty big step from here to here. Now we have more or less the same thing that we have here, but you start seeing some PMU displays used in the control rooms, and I don't know how many people have more than the SCADA EMS. I think some operators have security assessment tools based on steady state, but it's very few that have the dynamic stuff, right?
Now more and more, there are quite a few. At least in the US, there are about 9 to 15 companies which have that.
Yeah.
Fairly large ISOs also.
But would it be rather limited compared to the percentage?
I think so.
Yeah. So we're still, so you see, we still don't have a full transition here into more view, because it's only when you can take account of dynamics when you can actually predict things. Otherwise, I mean, it's pretty hard. Otherwise. So what's the future? I mean, this exists right now. This is the virtual control room of a Rolls-Royce boat that they use use to break ice. And the operator that has all sorts of information on virtual displays. So this looks like, anybody plays PlayStation? This looks like PlayStation, right? What does this look like? Atari. Okay, so that first part gives you a feel of the limitations that we have. And this other part gives you, on the measurement side, and this will give you a little overview of the challenges for modeling and simulation. So here you have a general approach to deal with physical modeling and simulation, okay? So, and this is the power system approach. Now, this is important. In a general approach to do this, the user, the individual, is both a modeler and an analyst. Why? Because considering the physical system that you want to model, you will derive the model, the first principles. From there you will derive the equations. And then depending what type of system it is, you can derive analytical and numerical methods. Or for problems that are too hard for analytical methods, so we have numerical solutions. But the individual, the modeler analyst, has to go here through this process. So it understands the simplifications and the limitations of the model that is posed. This is very different in our field. You have the physical system and the models are accepted by a lot of people, so people don't really understand the difference between a model and a software that they're playing with. So this is a specialized modeler with the domain-specific platform. I know very few people that are very, very good at programming a new model in PSSE. Why? Because you have to be familiar with the domain-specific platform. And within that domain-specific platform, you have hypotheses and simplifications that you have not made, that somebody else has decided. Well, the challenge there is that even if those things are affected, it is very, very difficult for you to know what is the effect of the model and what is the effect of the numerical algorithm. So there are some problems like numerical oscillations, simulation accuracy errors, and so on. But the problem is that because you're binding completely the tool, you're binding the tool with a specific solder, is very hard to extend these platforms. Especially when we think about it now, there's not a tool available to design a cyber-physical system. And this is one of the main problems that we're going to have. It's deep inside of the software. Okay, so in the general case, I explained that you could just formulate the problem from the model perspective. Here, if you need to add one, you need to use a user-defined model in the product for a specific language and have to deal with this issue. So at the end, the analyst has to be also specialized and know what are the limitations of this to be able to make sense out of it. So it takes many years for people to be experienced to understand the output of a PSSE result, for example. So you understand from here that there are some limitations. So I like to call, it looks like this, we're really brute force in the way of doing things. But it's actually because it has been like this for very long, and you guys probably know Bill Price. These are from the notes of Bill Price from the course that he used to teach at GE. This has not changed since the 1970s. We haven't attempted other approaches to do it. The core of what we do for modeling and simulation has not changed more or less since the 1970s. It's really important to understand that that has to bring some limitations to what we do today. Okay, so I'm going to skip this because I have spoken too much about it. But one important thing is that I want to make about here is because power systems have different time scales, we have come up with different solutions to do simulations, right? So when we are trying to do this, we make certain assumptions here, we ignore fast time scales, So we have specific software that has been developed under that paradigm. This should be like that because it covers everything, but that's another paradigm. And only the French have this QSS approach, but more or less this gives you an idea. So we have developed very specific ways of dealing with this problem. For the specific area of dynamics, which is what I work with mostly, we have all of these simulation tools which interpret the model attributes, which are actually just parameters, okay? Having parameters does not mean having a model. You can rarely exchange data without loss of information. And this is really relevant when you're operating an interconnection and you want to use different tools. If you want to use different tools, you have to get the same result, because otherwise, who's right? That's very important from the European context, where you have 52 companies that have to agree on something, technically. So you lose a lot of information. The simulations are inconsistent with a specialized human intervention. So if you want to have one tool give you the same as the other, good luck. So beyond these general descriptions, we actually need a common and unified modeling language that gives you a strict mathematical description of the models. And these are the kind of drawbacks that we get. But the effect of this is that it's very, very, very hard to take advantage of modern computing technologies. This is one example with end-user computing, and it's pretty difficult to get anything that is not standing on a laptop. Unless you have a special deal with the vendor, you can't go into a cloud. I mean, if you look at how people is doing things in other fields, they're exploiting cloud computing everywhere. We can't do that. There's not a single power system simulation software that you can run in a high-performance computer or in a cluster. So all the people working with biology and molecular analysis and so on, they can use that. In physics, they use it. But we can't. Why? Because our tools are limiting us. And we have to challenge this way of thinking in order to be able to evolve on how we can take advantage. But we shouldn't feel that bad. I tell people it's not such a big criticism, because this transition is being taking place in many industries. And you know why you are able to play Call of Duty, right? Because it was all developed by defense companies in reality. All of this, the way of dealing with the software. So actually they are somewhere here developing new network connected simulators when you are able to deal with these problems of standalone design. You don't use system-of-system integration approach. And the most important thing, you have no interoperability within tools. So even in the defense domain, which is the most advanced use of simulations in the world, they still have, they have seen this problem in the past. So we are somewhere here, and they are already addressing the solution. So it's very important to look at this sort of thing. There is in Europe right now a very interesting opportunity for evolution. That's a special picture for my North American talk, because since it's being done in Europe, you should ask, should we go in that direction? So the European Commission put a regulation, and it's written in the law that the network operators should use common transmission model. This is in the law, okay? With dealing efficiently with interdependent physical loop flows having regard to physical and commercial flows. So, market, a model that has all of the information of the market and the physical system. And this has to be used to support common network operation tools, okay? So that you can coordinate operation between different players in emergency and in normal situation. So this is a great opportunity because today you have software tool A and software tool B, and if you want to do anything, well, you get different results. This is a comparison between Eurostag, a French software, and another tool. I don't remember what we were doing there. It was an EMT model. So this is what is happening right now, that this mandate in standardization is setting up this model, and that's what you have heard now as SIM. CGMS is developing further the SIM to version 16, but it's very hard to develop it to be able to have consistent simulation results unless we add the attributes